Hello, everyone. My name is Peter Boza, and I work with Vision Analytical. And today we're going to be going over a short presentation and then some case studies related to fibers and different applications of fibers. And it's going to be covering the use of dynamic image analysis for this fiber analysis. To start things out, I guess the big question is, what is dynamic image analysis? There's a separate presentation that we have on dynamic image analysis, but I'll give you a quick, brief overview. Dynamic image analysis is a measurement technique that uses a high-speed camera. So as the particles go through a flow cell, we capture very high-quality images. These high-quality images are then converted into a binary image, and then we do a lot of different data calculations. Right now, a little bit over 32 or 33 shape measures we calculate for every particle. And we, of course, save thumbnail images for objective evidence. And it does comply with the ISO 13322. So one of the questions I do get sometimes is, with all the different techniques that are out there right now for particle size, why would we want to also measure particle shape? Again, a lot of very well-established techniques in the industry for particle size. Very good question. Why particle shape? The basic answer would be that not all particles are round. Most of the techniques that are in the industry will do a size measurement, and it's an indirect size measurement. And indirect size measurement basically means that it's not necessarily measuring the size of the particle, but some property that's a function of particle size. As a result, these indirect size measurement techniques will render histograms and particle size results of your sample, assuming the particles are round or spherical in nature. In many cases, this is okay. It's an established technique, works fine. But in the case of, especially what we're going to be talking today, fibers, I'm not sure if assuming they're round is a good idea. So as a result, dynamic image analysis has become a very complementary tool to some of these techniques, especially laser diffraction. Um, and many customers have expressed the use of, or the benefit of using shape in addition to these different techniques to measure particle shape for the flowability and packing compressibility of particles. So as you can see on the screen, if you have the cross-sectional area, those two arrows actually are the same, but the particles, fictitious ones that we're showing here, very different. So as you can imagine, in a process, assuming that you have a big mountain of the round particles, they're going to flow very differently as if they were, let's say, a 50-50 mix with the square particles. So understanding shape is very important for different processes. When it comes to dynamic image analysis and microscopy, those are considered direct measurement techniques. So the direct measurement technique does take an actual photo of the particle, and we can actually do a lot of things. Again, over 32 shape measurements, we can actually tell you size, assuming it's round. As you can see here, this particle, we're adding a model onto it that assumes the particle is round, and it's showing up as a 100 micron particle. So if you were to run this on an indirect measurement technique, you'd get something close to 100. But because this is a direct measurement technique, we also have the ability of doing 30 plus more shape measurements, which include length, width, aspect ratio, opacity, smoothness, many different measurements on every single particle, which does help, especially when it comes to fibers, where I think we need to do a little bit more than just look at size alone. So talking about fibers in general, I just did this quick search before this presentation. And as of this presentation, looking at a Google Scholar result of fiber shape and fiber morphology, there are millions of articles and peer-reviewed papers that have been written on the use of morphology, or the understanding or the implication of morphology on different types of fibers. And reading through this, I read there was different applications having to do with talking about tensile strength, talking about toxicity, viscosity impacts. So the morphology of fiber seems to be pretty popular these days. So once again, assuming these fibers, because they're not round, and assuming they're round in a with a technique that would assume it's round, it may be a little bit misleading. So if you could imagine, if we place this model around this model around every particle, and we assume this is a 10 micron particle, and this is a 11 micron particle, and this is a 10 micron particle. If you look at just the data, 10, 11, 10, it may be misleading because really these size only measurement techniques would not be able to tell you the difference if there was a 10 micron particle and it was this, or if it was this. So as a result, there are the different measurements that are made using dynamic image analysis that benefit fibers. One of them being, for example, fiber width. As you can see here, this model is being applied. We can actually measure the width of a fiber, even if it's curved. We can actually straighten it out for you and tell you what the width of it is, what the length of it is, and obviously what the aspect ratio of it is. There are other models that can be used in addition to just the fiber models. There are fiber curl, for example. So sometimes some customers want to know how curved these particles are. The more curved, the further away from the number one there is. So this straight fiber, as you can see, is closer to one. And as they get further and further away, more curved, we can actually calculate a fiber curl of every particle that's measured and tell you what that is as well. And there are other measurement techniques available as well. For fibers, for example, we can use Fourier width and length. These are caliper measurements. A lot of microscopists are used to these types of measurements. Again, we can measure for every particle. We do measure for every particle Fourier width, length, and aspect ratio. And we also have a bounding rectangle measurement, which gives you the width, length, and aspect ratio as well. And we do also measure opacity. So there are light particles and dark particles, and we can actually differentiate on opacity as well. So I just went over 10 different measurements that we do on fibers out of the 30 plus. So the question is, what do you do with all that data? Well, the reason we want to capture all this data is because we want to make sure that we have enough information on every fiber to differentiate one from the other. So in the case of these particles shown off to the right, this was for a customer who's making carbon fiber, this being a good piece of carbon fiber. But this customer, in the case of this carbon fiber application, as the fibers get stuck to each other, the more they are stuck to each other, the weaker the carbon fiber is. So in this case, this customer was more interested in determining what the histogram was, what the statistics were for the amount of particles that were single strand width versus, let's say, two or three strands versus many strands. So the fact that we actually can use, in this case, bounding a rectangle width or Fourier width or fiber width to differentiate one from the other, we can also quantify how many. We can determine what percentage were true single fiber strands versus multiple strands. Again, dynamic image analysis is a number-based technique. We can actually quantify and give you the percentages of those differences. Now let's turn to the case study. The case study that we're going to be going over is actually going to be a few different samples. We're going to be looking at some zirconia fiber samples and some milled glass fiber samples. We're going to be looking at some of the measurement techniques that we talked about a few minutes ago, which are the most appropriate for measuring fibers. And we'll be going over some of the different tools that the Insight has, looking for outliers and things like that, and also doing some comparative results. So let's switch over to the software now. All right, here's the first sample that we have. It's a zirconia fiber. So we look at all of the different statistics. Again, this is what most people are accustomed to looking at when they do a particle size analysis. They're accustomed to looking at either a number weighted distribution or a volume weighted distribution. One of the benefits of a number based technique is that we can actually look and see what percentages of populations there are. So, for example, let's say we want to see what these particles were greater than 50, let's say 48.6. We can actually look at the statistics to be able to see what that that amount was. So from 48 to 300, there was 353 particles, and the total cumulative was 10% of the entire population. We can then go in and say, okay, well, show me what those are. So I want to see just those. I can go in and now look at just those specific larger particles, and I'll be able to zoom in just to those larger particles. And we can go back and do several things. So yeah, one of the things we can normally do is go in and look at just the thumbnail images of all the samples, but that tends to be a bit overwhelming by searching just all the thousands and thousands of thumbnails. We tend to use thumbnail images as a final confirmation. So, for example, what we were just doing right now, where we were saying, okay, only show me the particles from, let's say, 30 to 100 or 50 to 100, and I can see what percentage there is, but then also go ahead and show me those thumbnails. Few other things that we can do. So, for example, we can actually, for fibers, we can actually do some comparisons of the width versus the length. So we can do a correlation plot. So in this case, we see that we have some width versus length. We have all a scatter plot of all the particles here. And as you can imagine here, the width tends to be in this general area because the particles seem to be all pretty uniform in width. Um, but then there's a small area down here. So I believe we're going to validate that with the images again, using the thumbnails to validate it. It looks like there are a large percentage of particles that are of a specific width. So the width seems to be very controlled, but the length is a bit all over the place, all the way from in the 30s all the way to 200 in some cases. But then there are some smaller particles, and I believe those smaller particles are chunks or little small pieces. Just to validate that, what we're going to do is let's look at a specific region. Let's look at an area of length anywhere from, let's say, 30 to let's say 30 to 50 microns in length, but a pretty tight width. We're going to look from 20 to about 30 microns in width, and then we can say, okay, well, this is the region that we really want to pick on. We're really interested in these specific area of particles for whatever reason. A couple of things we could do here. We can go ahead and look at the thumbnail images by clicking thumbnails, and then we can just move this out of the way, and we can see all the thumbnails that represent that small little area, which tend to be some of the smaller chunks, right? Some of the smaller pieces of those fibers. Kind of tells you a lot about the sample, that it looks like they're sliced or something similar to that. The other thing we can do is we can actually look at the statistics. So, for example, let's say for these particles in question, I wanted to see all the statistics just of those particles. So now, of those 276 particles that are in this little region, now I can see all the statistics just of that, what the opacity was, what the size was, what the fiber curl was, width, length. So that again, and like I said, the thumbnails tends to be a good way of referencing back. Um, the giving you some validation as to what the particles actually are. So I just restored the original. Let's go ahead and restore the original data and repopulate the chart. Do a quick little overlay where I can go ahead and do a comparison. And I had already opened these two, which is a Zirconia 1 and a Zirconia 2. These are two different samples uh, of the same nature, but they were two different samples. So it looks like there's a process difference between on the one and the other. So I opened these two, and I can actually do a comparison of anything. I can do an overlay based on size, number weighted. Let's go ahead and look at that. Yeah, and it looks like this first sample, which is the Zirconia 1, definitely has a higher population of particles that are bigger in size. Now, remember, size wasn't something that we're very interested in. Remember, it's kind of hard to tell and differentiate based on size. So what we like to do in this case is, because it's a fiber, we're going to look at some of the measures like bounding rectangle width and seeing if there's any big differences there, any bounding rectangle length, much bigger change there. We can actually do an overlay, all samples, and we could see that the first sample has a greater population of much longer particles, right? So less of the short ones, greater population of much longer particles. That might impact some flowability issues. If these particles are being manufactured and therefore, let's say, tensile strength, it could be that this sample is going to have a higher tensile strength because they're a bit longer. We can look at it not only by bounding rectangle, like I said earlier, fiber curl. Let's see if there's any differences in fiber curl as far as performance there goes. And it looks like, again, fiber number one has a higher uh, straight particles versus the other ones that may be not as straight. So these are just some of the comparisons that we can do with these different glass fibers for the zirconia glass. Now we're going to go ahead and do an opening of the glass ones. So here's the glass milled fibers. So looking at the run data, definitely here we see our size. Of course, the ones that we're more interested in are the fiber width. We can see that they're actually 20 microns wide, and they have a pretty broad span of length. Again, one of the first things that people generally tend to do is look at the thumbnail images, although there's so much more to it than just looking at thumbnails. That's actually a contaminated particle. So as you can see, all these glass fibers are somewhat translucent, but all of a sudden we see that this one probably a carryover from the previous one, previous sample of the zirconia was in there. One particle or a few particles isn't really going to make a difference in 20,000, but again, this is a good example of how this technique can actually capture rare events down to one particle. We may see a few more of them here and there, but for the most part, we see this is all the glass fibers. So these are pretty straight glass fibers. Very interesting. Again, we can do the same thing we did earlier, which is the correlation plot, and go through and just look at specific areas of the correlation plot. Uh, that's something that's very useful. Another thing we can actually do is look at particle classification. So with particle classifications, we can actually classify and look for specific populations. So I went ahead and filled out the names, long fibers and short fibers, and I just randomly picked Ferret length. And we're going to look at some of the particles that are long, 60 to 300 microns length, and some of the short ones, which are going to be 1 to 60. We'll go ahead and hit OK, and the particle classification window will come up. The particle classification window, one of the first things it does is it allows you to see different percentages. So there is some overlap here. That we could look at some other particles that were probably not classified under length, but you can see that it tells you certain percentages of each one. You can look at just the thumbnails of the long ones, let's say. That was a pretty thick one, but long. And then we can also look at, let's say, let's put length. I think it's very length. For the short fibers, we can also do the same thing and confirm that those are the short fibers. Uh, So again, there's a bubble, and there's going to be some particles that are going to be classified outside of this, so don't show up in the percentage of total because I only picked one statistic. Uh, so there's a few different examples of how we can do some comparisons. Again, the benefit of having the all of the different measurements, all of these different measurements for every single particle is to be able to, again, differentiate a specific population from another. Again, it's also very important to understand that because these different shape measures are available, it gives you a much better understanding and a easier way to understand your particles, especially when it comes to fibers. Again, assuming particles are round, especially when it comes to fibers, is going to be a bit misleading. That's where I think dynamic image analysis is a really good solution. It's a direct measurement technique. That's it. Thank you for being so patient and listening to me for so long. If there's any questions, please feel free to reach out to us either directly on our website, LinkedIn, YouTube, or just email me directly if you'd like. I look forward to hearing from any questions that anybody may have. And thanks again.